Yeah, thanks. So today's a bit of a special day for me. So 10 years ago, I was a freshman in physics here in Leiden University. And I remember that I wrote my first game-playing AI in an introductory programming course by Walter Kosters. Now I'm at New York University. And it's really nice for me to be back here and present what I've been working on in the meantime. Okay, so this is a project that we like to advertise as "Do People Think Like Computers?" with varying degrees of success. What we really do is we're using artificial intelligence to understand how people make decisions when playing combinatorial games. So first of all, why do we want to understand how people make decisions? I'm a neuroscientist, I want to know how people think. Second question, why study games? It's a classical argument, we heard it two talks ago. The complexity of games make them a good proxy for hard real-life decision problems such as navigating, negotiating, designing PowerPoint slides, things like that. And it's this complexity that's really crucial for us. So in neuroscience and psychology, we know a lot about the neural and psychological processes underlying decision-making. But most of the decision-making tasks that we use are very simple, like, would you like $10 now or $20 next month? There does exist some work on more complex games, such as the centipede game, but in general it's not clear how to, whether our knowledge about elementary decisions can be generalized to understand complex games reminiscent of real-life decision problems such as chess. So our goal is to bridge this gap, to find a game which is complex, but we can still understand human behavior quantitatively. What we've been working on are MNK games. So an MNK game is played on an n by n board, and you have to make k in a row. So you all know one of these games, like 3-3-3 is just tic-tac-toe, and we've been using 4-9-4, so you have to make 4 in a row on a 4x9 board. If you haven't seen this game before, here's an example played by two people in our lab. Okay, so white is spotting the threat there. White is playing quite defensively. So black is taking the initiative and keeps getting the initiative. That's not a very good move. Because now black. Yes. Okay, so as you can see, human behavior here is it's sophisticated. I mean, people do make some interesting long-term moves, but people also make very obvious mistakes. Okay, what I'm going to do today is three things. First, I'm going to describe a AI algorithm that we have designed to mimic human thinking in this game. The algorithm will have parameters, so settings that you can tune, and we're going to estimate the best possible settings for every individual player. We're going to validate that this model actually describes people's thought process by predicting their moves. And then we're going to ask, well, if I have two players, and I know that one is stronger than the other, like, how do those parameters that I infer, how do they differ? Okay, so I've become recently aware that player modeling is actually quite a big field within AI. But there are a couple of differences between the existing literature and our approach. So typically, or from what I've seen so far, player modeling in AI is often done in complex games, whereas our game is quite simple. Player modeling also often uses expert players, large data, and you aggregate all the data together before you estimate the best settings for your algorithm. We are going to be using novice players who've never played the game before. We have small data, we have only 138 moves per player, and we have only 40 players. And we're going to fit individuals. Now, there's one more thing which I haven't put on the side, but that's actually a really important philosophical difference. We actually want to interpret the best fitting algorithm with the best fitting parameters as a description of the person's thought process. Right? So I'm not just saying, oh, I want to predict your moves, I'm actually saying, I interpret that as describing how you actually think. Okay. So the second question, how do strong and weak players differ, also has a lot of literature behind it from the work on expertise in chess. specifically, do grandmasters think further ahead? How far do grandmasters think ahead? And is it more than club players, for example? So there is some literature on this, but the evidence is sort of mixed. So we thought it would be interesting to answer this question in our game. Okay, so let me start. Explain the AI algorithm that we're using. It's going to be a heuristic search algorithm guided by an evaluation function. So the evaluation function is, let's say this is the position and I want to know who's better. Well, I see black has 3 in a row, that's probably good. Black also has like a 2 in a row there with 2 adjacent pieces, that seems good. Another 2 in a row there. This is 2 in a row with like non-adjacent pieces, that's probably also good. Furthermore, I'm going to count the number of pieces on the 12 central squares, because playing in the center, as in many games, in this game, is strong. So black has 1 more center piece than white. Now, white doesn't really have any obvious features of interest, so I'm going to say black is good. Formally, what we do is we have a set of features which are illustrated here. Each of them has weights assigned to it, and I just take a weighted linear sum of those features of myself minus the opponent. Now, all of the weights here are going to be parameters that we infer. The features are fixed. Okay, so then we're going to do a search algorithm guided by this evaluation function. This is going to be straightforward, best first search, minimax updates. One maybe non-standard thing, in the expansion step, we do some pruning. So suppose I have this position which I expand, I come up with a number of candidate moves, I evaluate them with this evaluation function. Everything that's worse than the maximum minus some threshold, I'm going to prune from the tree and never consider. So note that this pruning can actually be detrimental. So contrary to things like alpha beta pruning, it could actually be that this was the correct move, but you prune it right away. Then the other thing is, well, I've described to you how like each of the steps of the algorithm works, but of course I also have to tell you how long we go. So the amount of iterations that you go into the search process is random. What we do is after every iteration, there's a constant probability that that one is the last. Right? So you do an iteration, is this the last? Yes or no? Then there are more sources of variability. So it's sort of important for me to emphasize that we're not trying to build a good AI here. Building a good AI is really simple. It took me like about 2 days to build a program that can beat myself. Right? The game is really simple. What we're trying to do is to mimic human play. So we have to also add in sources of mistakes. So one of them is just blunders, completely random moves. Then sometimes, as you saw in the game that I showed, a player might make a reasonable move but overlook some kind of obvious pattern. So these attentional lapses, we model by dropping, when we count features in the evaluation function, you just you skip particular instances of that feature. Finally, after we calculate the evaluation function, we just add Gaussian noise. Right, so now you might say, okay, I don't really see anything like innovative or novel on this slide. And you would be right, and this is intentional. So our idea is we want to build a psychologically realistic AI algorithm to mimic human thinking. So every choice that we've made is either supported by AI literature or psychology literature, and often both. I haven't pointed out the references, but there are papers for sort of all of these. Okay, like I said, the model has 10 different parameters. There's the weights of the features, there's the threshold for the pruning, the probability of stopping, which translates to, on average, how big of a search you build, and the various sources of noise. Like I said, we're going to obtain these parameters for individual players, and we do this by maximum likelihood estimation. A little technical aside here. Maximum likelihood estimation is common in statistical inference and machine learning. It's important that the likelihood is the probability for the agent, for the model to make the same moves as the player did. It's important that we maximize the likelihood instead of, for example, just like the accuracy, because maximum likelihood estimation requires you to have a probabilistic prediction. So to get a high accuracy, I have to know in every board what your most likely move is that you're going to make. In order to get a high likelihood, I have to know the full probability distribution of moves, including, well, if you are not going to make the most likely one, which other moves are you going to make? What kind of mistakes are you going to make? Okay, so this is what we get if we do the estimate. So I'm going to play you the same movie again. Now in red, I show you the prediction of the model. So the model is reasonably confident that, oh, wow, that was good. Note that the color still only goes to 60%, right? So it looks better than it is. The model, okay, here it gets it kind of wrong. I'm happy with that one. Okay, I mean, this is easy to predict, of course. But note that even now, I'm not 100% confident that white is going to move there. Because sometimes white doesn't. Okay, and of course the model predicts that when you can win, you win. Oh. Okay, well, maybe some of you might have seen the message on the bottom of the slide. On average, we get about 40% of people's moves correctly predicted. Now, to sort of understand whether this 40% correct is good, I'm going to compare to some alternative models. The first of which is what I call the Opheusden model. It's an oracle model which always makes the objectively correct move, but sometimes it just makes a blunder, a completely random move. Now, if you fit this model, the blunder rate is a parameter that you infer for different players. So this model can capture your objective frequency of making mistakes, but it can never explain subjective preferences between moves that are objectively equally strong. I also trained a convolutional neural net to predict players' moves in this game. Because we have such a small data set for the convolutional net, I have to train on aggregate data, but I can still predict for individual subjects. So then what I'm doing is, this is something like neuroscientists like to call lesions. It's essentially you take your model and you just remove a particular component from it. And then of course you fit all the parameters again. A special case of this is the myopic model, which doesn't do any search. It just has the heuristic function, as I described, and the same sources of variability. Okay, so here's the first main result. Okay, in this figure, which is maybe slightly non-standard, every point is a player. We have 40 players. And I'm plotting the log likelihood of the main model versus the log likelihood of the operand model. The log likelihood is a measure of goodness of fit. The higher it is, the better your fit. And it's always negative. So the points lie below the diagonal, meaning that the main model fits better than the operand model. Okay, is that clear? Because I'm going to have a couple of more of these. So now I'm plotting the main model against the convolutional net. Again, the main model is better, but the convolutional net gets close. The main model versus the myopic model. Okay, so now the difference becomes really small, but still, if I take the average of the difference in log likelihood, the main model wins out by a little. And here are all the models. So I've shown you these before. Oh, sorry, I should explain the figure. So now I'm plotting this log likelihood difference relative to the main model. So here's the main model at 0, by definition. And here are all the other models. So this one is bad, this one's bad, this one is reasonably okay. And all the lesions, except maybe the no center, are worse than the main model. Okay, let me... So this result is really nice, but there's sort of a caveat here. The only thing I'm telling you here is that this is a better description of the data than, for example, this one. But it could still be that all of these models have some consistent mismatch with the data, that they're all bad in a particular sense. One way to test for that is to calculate summary statistics. This is essentially you take your data, you project it onto some kind of statistic, and you just visualize the prediction as well as the data itself. So here I'm plotting as a function of number of moves played into the game, how far away from the center does a player move, how many pieces are there on squares next to the move where a player moves, and how many threats do you make. The specific of these summary statistics don't really matter. The point here is that the orange and the cyan curves almost lie on top of each other. So the prediction and the data match very nicely. Okay, we can do some more analysis, but I want to go on to the next experiment. So before I explain this experiment, let me reiterate the claim that I'm trying to make. So let's say I have two players. Let's say Chris and Benny, and they play against each other for 1 hour. What I can do is I take all of Chris's moves and I use my algorithm to extract 10 numbers, 10 parameters from Chris's moves, and those 10 numbers fully characterize Chris, at least from the perspective of predicting his choices in future games. Everything I know about Chris is like encoded in those 10 numbers. This is already a strong claim, but if those 10 numbers actually reflect Chris's thought process, then I should also be able to generalize and predict his choices in other tasks. So what we did in our experiment is first, well, we didn't use Chris and Benny. We used players who play against computers, and then they had two additional tasks. One is a binary choice task. I say, here's your board, you have two options. You have to pick between these two. You cannot move anywhere else, even though you might think that that would be nice. And a board evaluation task. So I show you a board, I say, on a scale from 1 to 7, are you losing or winning? Okay, so here are the results for the binary choice task. So what I've done is I take a player, I take their moves during the game against the computer, and then I'm going to use those parameters to predict what the choices that you're going to make in the binary choice task. Okay, so the way this figure works is every dot again is a player. I've sorted the players to make it look nice, but in principle the ordering here is meaningless. For every player I just plot like how many of your choices I can predict correctly. Of course, predicting 50% would be easy. For most subjects, I actually get more than 50%, and the average is a little bit below 60%. Okay, is that good? I mean, it's more than 50%, which is good, but how good could you in principle be? Now, I've designed the positions that I've shown in this experiment to be difficult, for both of the options to be like roughly equally good. And if players are truly indifferent between those two options, they might just choose randomly. So what I'm trying to say is there is an upper bound on how well you can predict a player's moves, set by the intrinsic variability of that player. And unfortunately, we cannot measure that bound, because I never show the same player the same position twice. But I'm now going to do two controls to kind of get at where this upper bound might be. Okay, so like I said, the model gets about 59% of players' choices correctly predicted. So now I'm also going to ask, well, if I had an oracle model, a model that always makes the best move, again, when both moves are equally good, it just picks randomly, and I use that to predict what people are going to do. This oracle model will also, I mean, if you have some inherent variability in your choices, this oracle model will also suffer from that same variability. The oracle model does worse. Okay, so that's kind of nice. Another control that I did is I use the mean across subject. So essentially what I'm doing is, well, Chris does the task, everybody else in the room does the task as well, and my prediction for Chris is the choice that the majority of the room makes. Now, if I do that, I can actually predict Chris's choices reasonably well, about as well as my main model. Right? So this is not a fundamental limit of how well you could predict, but it might be a good estimate. I can gain even more insight if I split up this percent correctly predicted by the objective values of the two options that I'm giving. So first of all, if the two options that you're presented with actually have objectively different values, so one is winning and the other is drawing or losing or draw loss, all three models get like above 60% correct, and it's not really clear which is better. Now, even more interestingly, if I focus on the cases where both of the moves are objectively equally strong. Okay, so now an oracle model can never predict your choices because it just moves randomly. The oracle model doesn't do anything. The mean across subjects and the main model are, comparable. Next up is the board evaluation task. So here I do the exact same procedure. I infer parameters from the moves that you're making in your game, and I predict the evaluation scores that you do in this task. Is going to be the correlation between the predicted and observed evaluations. So 0 here is a null result, and everything higher than 0 is good. And again, for all but 3 subjects, we're above 0. Again, I can do the same thing. If I look at sort of the 2 controls, they're comparable to the model, which lends credence to the hypothesis that maybe we just explain all the variability that there is to explain. If I split it up by considering only the winning, only the drawing, or only the losing positions, again, the oracle model cannot do anything, and our model gets as well as we can get if we knew what other people do. All right, so now I get to the third part of my outline. How do strong and weak players differ? So now what I do is, let's say I have that 1 hour of games between Chris and Benny, and I observe that Benny is a stronger player. Sorry, Chris, but suppose I observe that Benny is a stronger player, and I infer those 10 numbers for both of them. How do those 10 numbers differ? Which ones are going to be higher? Now,
do you like questions, or do you like to finish your talk? Because we are, I would say, a little bit constrained. Your talk is very interesting. Let me say that. There's no doubt, but I cannot make exceptions.
You can ask questions if you want.
What?
You can ask a question if you like.
I have not a question, but for the public, I mean.
Oh.
That is the question. I cannot give you. Cannot give you 10 minutes anymore. That is the thing. Okay. So I'm myself in trouble. So I've listened very, very captured. So no way of that. But
yeah, if you want to ask.
So has this game been solved? It looks like it might be on the border of.
Yeah, we did derive the optimal player. So when I tell you objectively win, objectively drawn,
it shows unsolved. It shows unsolved on the Wikipedia page, but I wonder if it was recently solved.
Yeah. So a previous student in the lab. So we didn't completely solve it. We know that if the first move is in the center, then you can force a win. But we don't know the optimal move in every single position. But so we don't have a strong solution, but it's weakly solved. That was a long answer to a short question.
Let me interview a little bit. I know that there are some connoisseurs in the audience, so if there are people who would like to have questions, I don't know, 2 by name or 3. Yeah, yes?
Well, since this is out of talk, I'm interested in a summarization of how you answer how do strong and weak players differ.
Okay, this is a continuation of the talk.
Well, it's a summary. What's the punchline for the section that we don't get to
the audience is the boss, as you understand. So
okay, I mean this won't take very long. Okay, so there are 3 reasonable, given the parameters that we have, there are 3 reasonable hypotheses.
What's the best? What's from your experiments? What's the summary answer to?
It's going to be both of those. But I mean, let me just. This won't take more than 1 or 2 minutes. So there are 3 reasonable hypotheses. One is the amount of variability might be different, right? So stronger players might be more reliable than weaker players. Stronger players might build. So 2 parameters relate to the size of the decision tree. Stronger players might build larger trees, which in non-degenerate cases will make you stronger. Or they might have better finely tuned weights. So the first hypothesis I can definitely confirm. So again, every point is a different player. I'm plotting the ELO rating of that player versus the move entropy, a measure of the variability in their choices. And there's a very strong correlation, right? So the most variable players are very weak, the stronger players are much more reliable. This is, I guess, the punchline slide that you're looking for. The move entropy correlates pretty really strongly with ELO. Tree size also. Depth of search not as much, although it's close to being significant. And the heuristic function quality, which is sort of a measure of how good your weights are, doesn't correlate at all. Okay, so let me summarize. Do people think like computers? So I had wanted to say yes here, but then my advisor said that I couldn't. So I just say I believe so. So the evidence that I've shown you is an AI-inspired model with not that many ridiculous assumptions, can predict people's choices, can generalize across tasks, and can explain differences in playing strength. Those differences are that stronger players calculate more, larger trees, and more precisely, less variability. However, we do not find evidence for deeper search or more accurate heuristic functions. In the future, we want to validate our model by predicting response times, eye movements, and neural activity measured with an fMRI scanner, because we are in a neuroscience department. Now, I have two questions for you. One is, can we improve the model with more realistic AI? And we definitely want to test our model in a different game. So which games should we try? And these are my collaborators. Thank
you. You know we have question time. I allow 3 questions. So who would like to have the floor?
One question about blunder. The way you define blunder on the screen seemed quite inaccurate. You said a random move.
Yeah.
But I think a blunder, in essence, is a really good move if there wasn't a specific feature like the opponent threatening to win somewhere. That would have been good absent that feature. It's not that when I blunder in games, which I do all the time, I suddenly think, let's not think and make a random move. It's like, oh, I have this amazing move. Oops, I didn't see that.
Yeah, so I think what you're describing, so maybe it's a terminology issue. I think what you're describing is what the attentional lapses would do. So an attentional lapse literally does that. You eliminate one feature from your evaluation function, so you don't notice that one, and then you go through search and the whole process in order to determine what move you would make. So it is like the best move that you would have made in lieu of that particular feature. Yes?
How much data did you collect for the actual players?
So in here I have 2 experiments with 40 players each, and in both experiments we have about 150 moves per game. So we have 12,000 moves in total in all of the data.
So how 150 moves per game?
No, sorry, per player.
Per player. How many games were that?
Okay, so now the numbers don't. It differs between the 2 experiments. With a game, on average, will have 17 moves, counting both players, and there are, on average, I think 16 games per player. I think if you do the math, that should work out. I'm trying to do it in my head, but I can't.
Last question. Yes.
So did you try some kind of Turing test? Is this game played by a computer or by a human?
I really like that suggestion, and actually I sort of did. I had one person play against either a person or my computer, but because of the way I set it up, I was trying to do this on my laptop, and like I was there in the room and I was trying to hide, my knowledge of who they were playing against, and I failed. So we were able to fool the subject 2 times out of 8. But we're actually thinking of doing like a real Turing test, and that would be a really strong test of the model. I mean, if people are really unable to see the difference between a computer and a player here, that really means that we've captured their behavior.
Okay, Bas, thank you very much.
Yeah,
You did a very good job in Leiden again.